Welcome to this explainer. Okay, let's just dive right in. Today, we're exploring the elegant logic behind a classic algorithmic challenge, the merging communities coding problem. If you've ever wondered how massive networks efficiently track and connect distinct groups of users or data points completely on the fly, well, you're in the right place. We're going to break down the exact data structure that makes this possible. And trust me, the optimizations we'll look at a bit later on are absolute game changers.
Here's a quick look at our roadmap. We'll start with the community problem, introduce the union-find structure, and break down the core union and find operations. After that, we're going to level up our solution with two major optimizations, union by size and path compression, before wrapping it all up with performance and complexity.
All right, Section 1, the community problem, forming groups. We're starting with a very relatable scenario, individuals forming groups. So imagine you have a set of n completely isolated people, numbered from 0 to n-1. Initially, everyone is essentially just hanging out in a community of one. Our goal is to write a system that handles two specific things. First, we need to be able to connect any two people, say person 0 and person 1, and when they connect, their entire respective communities instantly merge into a single larger community. Second, at any given point in time, we need to be able to query our system and instantly retrieve the total size of the community that any specific individual belongs to. The real challenge here isn't just making these connections, it's doing it incredibly efficiently as the network scales way, way up.
Moving on to Section 2, introducing union find, which is also known as the disjoint set union.
To actually solve this puzzle without our system totally bogging down as it grows, we're going to use a data structure that's perfectly built for the job, the disjoint set union, or as it's more commonly known, the union find data structure. As the name heavily implies, this structure manages sets of disconnected elements using two main actions. You've got the union operation, which takes two elements from completely different sets and merges those sets together. Then you've got the find operation, which just figures out exactly which set a specific element currently belongs to. So in the context of our problem, union connects the communities, and find helps us figure out whose community is whose.
Okay, so let's think about how we actually structure these distinct sets under the hood. To make union find work, each community elects a representative, basically a community leader. We can model these communities as directed graphs. Instead of every single person having to keep a massive, exhausting list of everyone else in their group, every person simply points to the leader, either directly or indirectly. For instance, person 0 might be the representative of the left community, and person 2 the representative of the right one. Everyone else in that community just points upstream toward them.
Before we go any further, it is absolutely crucial that we distinguish between someone's immediate parent in the graph and the ultimate representative of their whole community. A person's parent is just the very next node they point to in the chain, but the representative, that's the ultimate root node at the very top of that entire chain. The representative is literally the one person in the community who points to absolutely no one else but themselves.
Section 3, union and find operations, merging and searching. Now that we have that mental model down, let's actually look at how we merge these groups together in code.
The union operation follows three highly logical steps to combine two sets. First, you take the two people who just connected and you find their respective community representatives. Second, you pick one of those two representatives to become the new overarching leader of the combined group. And third, you just connect the other representative directly to that newly chosen leader.
Let's look at this in action. Suppose person 1 and person 4 decide to connect. We can't just draw a line between them and call it a day, right? We have to first identify their community leaders. So we use our find function to trace up the chain from person 1, discovering that person 0 is their representative. We do the exact same thing for person 4, tracing up to find that person 2 is their representative. Now we know exactly which two overarching communities we're dealing with.
Now, before we actually make the merge, let's consider the naive approach. If we pick person 0 to be the new overarching leader, we could manually go through every single person in person 2's community and just reassign their parent pointer directly to person 0. Sure, it creates a nice flat graph, but think about it. What if that second community had 1 million people in it? Updating 1 million pointers just because two individuals connected is wildly inefficient. It would grind our system to an absolute halt.
And this is exactly what brilliantly illustrates the elegance of union find. The true aha moment here is that we completely bypass all that heavy lifting.
To merge the entire community, we literally just take the old representative, person 2, and set their parent pointer to the new representative, person 0. That's the whole shebang, one single operation. Because everyone in the second community was already pointing to person 2, they're now all indirectly connected to person 0. The communities are merged instantly.
But wait, how exactly do we locate these leaders to begin with? As I mentioned, the find operation does this just by walking up the parent chain. If we want to find the representative for a node, we check its parent. If that parent isn't the root, we check the parent's parent, and so on, traveling up the links until we hit the person who is their own parent. That self-pointing node, that is the definitive representative of the community.
This whole elegant logic can be captured in just a few simple lines of recursive code. We basically just ask, hey, is node X its own parent? If the answer is yes, awesome, we found our leader, and we return X. If the answer is no, we recursively call the exact same find function on X's parent. It's an incredibly clean, straightforward way to traverse the graph upwards.
All right, moving to section 4, optimization union by size. First optimization. Our basic union and find structure works, but as our communities grow and merge repeatedly, a hidden flaw starts to pop up that we absolutely have to fix. Let's see what happens when things get lopsided. Look at what happens if we merge a massive community into a tiny one. If we just arbitrarily choose the leader of the tiny community to become the new overall representative, we just took the massive community and awkwardly attached it underneath the small one. This forces a huge number of people to now have a significantly longer path to reach the ultimate leader. We're unnecessarily elongating the chain, which makes all our future find operations slower for all those people. Not great.
To evolve our algorithm, we implement our first major optimization, union by size. The rule here is wonderfully simple. Before merging, we check the total size of both communities. We then strictly enforce that the representative of the smaller community must be attached to the representative of the larger community. By doing this, we guarantee that only the folks in the smaller group have their distance to the leader increased by 1. The larger group's distance remains completely unchanged. This keeps our trees as shallow as possible. And conveniently, tracking these sizes allows us to instantly answer our original problem's requirement of returning a community's size.
Section 5, optimization, path compression. Second optimization. Union by size is fantastic, for sure, but we have one final, absolutely brilliant trick up our sleeve to make this algorithm practically blazing fast.
The reality is that over a long period of time, with complex, unpredictable merges, graphs can still get a bit tall. Think about nodes 3 and 6, way down at the bottom of a structure. If we call our recursive find function on node 3, it has to hop to node 2, then node 1, before finally reaching the representative, node 0. That takes time. And if we have to do that repeatedly for nodes deep in the tree, we're just wasting computational cycles.
But remember the true magic of recursion? Once our find search reaches the top and finds node 0, it has to pass that answer back down the chain to exit the recursion. On its way back down, it actually tells every single node in that chain, node 1, node 2, and node 3, exactly who the ultimate leader is. They all get the message, the root is node 0.
Well, we can use this return journey to our massive advantage. Instead of just passing the message down, we actually update each node's parent pointer along the way. We tell node 3 and node 2, hey, stop pointing to the middleman, just point directly to node 0. This technique is called path compression. During a routine find call, we brilliantly squash the entire graph flat into a highly efficient star shape, so the next time we call find on node 3, it's a single hop.
Finally, section 6, performance and complexity, complexity analysis. We've designed the structure, we implemented union by size, and we added path compression. So what's the final payoff for all this?
The payoff is pretty monumental, because path compression completely flattens the trees and union by size prevents them from getting excessively deep in the first place. Our time complexity for uniting groups, finding leaders, and fetching community sizes drops all the way down to amortized O of 1. Practically speaking, this is essentially constant time execution, regardless of how massive the network actually becomes. To achieve this, it only cost us O of n initial setup time and O of n space complexity to store our arrays for parents and sizes. It's honestly a masterclass in algorithmic efficiency.
We literally took a problem that could easily bog down a naive system and transformed it into a lightning-fast, amortized O of 1 powerhouse. With an algorithm this ridiculously fast and beautifully elegant, it kind of makes you wonder, Beyond merging basic communities, what other massive, real-world network problems is the union find structure secretly powering right now? Keep that in mind the next time you see complex connections happening instantly on your screen. Thanks for joining me on this explainer, and keep exploring.